And let me also share the screen. Allow. So this we just do it as a function. Define. Okay, so what's nice about Colab is that they will guess from the context of the Jupyter notebook, and then they will try to fill something reasonable. So that's doc string, right? So basically that's the string for if n equals to, usually you can say the base case can be 0, can be 1. So when it's 0, you're just multiplying 0 factorial. You're not multiplying anything, but you can make it a 1. That's the base case. Okay. And then every latter factorial would rely on the prior. So if you go back to the formula right here, it's n factorial. The factorial with input n relies on the factorial of the previous. Okay, then times that n number. So you just use the return n times the factorial of the previous. So that's the idea. And of course, if you want to make sure that the function is reasonable, you can also say if the input is if type n is not a string, then excuse me, not an integer, then pop an error, and or if n is less than 0, then also pop an error because the negative inputs are not legal, right? But you can say return error message. Okay. Here, input should be integer, non-negative integer. Okay. Let's do that. And here, elif and else. And let me also make sure that the number is tested. Okay, factorial of 5. Let's say 4. So you should expect what? 2, 3, 4 is 24. All right, good. So now the recursion here basically your factorial n relies on factorial n minus 1, and n minus 1 would rely on n minus 2, and just all the way down to, so every time the input will decrease by 1, all the way down to 0. Okay, when 0, you are not calling any prior cases, right? And of course, you can also utilize more base cases if you want to, if you wanted to run a little bit faster, but it's going to be a trade-off. Okay, so later when we look at the implementation of calculating the ratio between Fibonacci numbers, then that loop will be very time consuming, and you will see why really soon. So far so good. All right. So of course, if you want to write it in iterative code using loop, that's totally fine. Here is a while loop. If you want to use it as a for loop, it's also fine. So what you do here is that basically for j starting from 1, ending at n, you just every time multiply that j to the product, right? So you can name it as total, you can name it as product, it doesn't matter. That's just a variable name. For if you usually total is for sum. You can say product. Okay, products initially equals to 1, and every time you multiply product with j, and then every time you increase j. So here for while loop, you have to increase the index every time. But if you are writing a for loop, then you don't really need to do that, right? So just remember. So there are choices that you can do. Okay. So, and then you can also think about how many lines this kind of procedure has executed for a particular input. So every different implementation will behave a little bit differently. All right. So let's also look at the Fibonacci sequence. So the idea here is yeah. Let me switch back to the notes. So the Fibonacci sequence is very important in the sense that you have a sequence that's relying on the prior two cases, n minus 1 plus f n minus 2. And here we have two base cases, right? Because now you need f0 and f1 in order to calculate f2. So f0, f1, they are usually defined as ones for the original Fibonacci sequence. But if you want to change the initial numbers, and then the behavior of the sequence may behave slightly a little bit differently. But as you know, that this kind of recursion in formula is actually, um, I think there's a term, quadratic recursion relation or something. Basically, um, the explicit descriptions for each term will rely on the roots of a quadratic equation. Okay, but yeah, that's sort of like a digression. If you want to code it, however, so if you don't really want the explicit formula for each term, but you just want the numerical value, that's actually not difficult. So what you do here is that, okay, for 0 and 1, they are the base cases that return you ones. But every larger index n, they will rely on the prior two. So if you're writing a recursion, that's really straightforward. Okay, so these are base cases. And this is the recursion formula. So now if you think about the Fibonacci sequence, Fn relies on Fn minus 1 and Fn minus 2. And then Fn minus 1, the Python interpreter would then say, okay, I need to compute that. So what does that rely on? So that rely on f of n minus 2, Fn minus 3. So now you see these is kind of repeated, right? And then this one relies on Fn minus 3 and Fn minus 4. So it just goes all the way down. Okay, so unfortunately, you have two sequences to track, and every time it branches into two. So it's a little bit more computationally troublesome. Okay. So and then here, if you write this and implement, indeed, you would be able to calculate the correct Fibonacci number. And just like what we mentioned earlier, so Fib 13 actually relies on 12 and 11, and 12 relies on 11 and 10, and 11 relies on 10 and 9, and it just goes down. It branches like in terms of a large tree. Okay, so and here, so we are now sort of using this kind of abstraction. So you have the function defined, then you don't really care about how the output is computed. You just know, okay, for whatever input that I provide, that black box will give me my desired output. And then you can reuse this function, okay, like this. So here the test fib function is basically saying I print the list of outputs. Okay, because now every time, so if you just look at the Fibonacci sequence, if you give me an input, I give you an output. This is not so efficient in terms of looking at the sequence overall. So here you can write as you can write this kind of test fib sequence to function to print out, let's say, the first n terms within the sequence. So that's what this function does. So we don't really have to. Let me see. Okay, so yeah, let's take a look, because here we can also play with changing the initial values, and that will give you different sequences. That's commonly seen in this kind of recursion relations. But let's quickly play with that. So let's try. So let's try the yeah. So the execution here for inputs that's not really large, this is really efficient. Okay, so we're printing what? We're printing F0 all the way down to F12. So that's pretty efficient. So now if I slightly change the initial terms like this, okay, so let's say my F0 is still 1, but let's change it to something, let's say a 4, okay, for F1. So that tells you what? It tells you F0 is 1, F1 is 4, then F2 is 5 expected, and then it just it's going to be a completely different behavior. Okay, so 1, 4, 5, then 9, 14. So basically, the rule of recursion is still the same. However, the sequence resulted from is completely different. Okay, and of course, that's basically how recursion works. And then if you want to go back, then just make sure that. So I don't think I really need to do that. I just change this to 1. That's totally fine. All right. Okay. So now, what's really nice about Fibonacci sequence is that the ratio, okay, between the adjacent Fibonacci terms is gonna give you what's called the golden ratio. So if you use Fn over Fn minus 1, this ratio would converge. Okay, so this now if you're looking at this procedure right here, so let's see if it, that's pretty quick. So let me try some number a little bit larger, 30. Okay, so now it takes a second, okay, to run. So what's the problem here? So here, if you're looking at the code, it says what? It says for every I from range 31. So 31 is basically saying I'm doing the ratio from when I is 0 all the way up to 30. Okay, so 31 cases. For each such case, I do fib of n plus 1 over fib of fib of I plus 1 over fib of I. So basically, I'm using the next term, the next Fibonacci term to divide by the current. So remember, I starts from 0, so you would have to make this input legal. Okay, so that's what's natural. So now, if you look at the ratio, okay, so it's gonna get closer and closer and closer, and really stabilize at this number here. Okay, so that's what's called the golden ratio. And the thing here is that if you think about the mathematical derivation, actually it's rather straightforward. But now think about the procedure right here, that it runs for about a second. Let me see. So what's the problem? Yeah, 1 second. Okay, so this is much longer than usual implementations. Why? Because if you're thinking about let's say the last line, okay, the last line is fib of 30 over fib of 31 over fib of 30. Okay, so if you are calculating fib of 31 over fib of 30 and getting this ratio, you are actually computing fib of 30 and fib of 29. fib of 30 and fib of 29 independently. So when you calculate fib of 30, you need 29 and 28. And then 29 needs 28 and 27. 28 needs 27 and 26. And basically, it's a tree that branches all the way down. And then for the prior fib number, fib 29, the computation is sort of wasted. And you have to do it all over again. So this is definitely not super efficient. So of course, so this is the kind of like a trade-off. If you do it in a really abstract way and you are computing latter terms of the sequence, then it will trace back and form a tree, especially for this Fibonacci sequence. So another method or another idea is that, okay, I just construct the Fibonacci sequence from F1. So F0, F1, I know they are ones, okay? And now for F2, I calculate it and store it in a list as the third item. And then I just move on. Every time I just do what? I just do the adjacent two last elements and do an addition and update to the next element. So that's really cheap, right? And then I would just need to somehow store everything up to 30th. So there's a trade-off. So in this for loop, this kind of setup, you would need to store 31 terms. The addition will be really efficient. So that the ratio computation is also efficient. However, you would keep the thing in the memory. So let's say if you want to compute a million terms, of course, doing 1 million terms for the abstraction, okay, for the recursion will be super expensive, super slow. But if you are doing 1 million terms of Fibonacci sequence in a loop, then you will need to store 1 million terms. Okay, so that's the trade-off. All right. So but unfortunately, we haven't touched what the list is yet. So we're going to talk about that in the future. So now here, let's quickly look at the ratio. Okay, so a little bit of the mathematics. So essentially, what do we see here? We see this is f of n over f of n plus n minus 1, right? So here, remember, by definition, this is fn plus fn minus 1 over fn minus 1. Wait, I need to change the indices. N minus 1, n minus 2. Okay, so this now, I notice that fn minus 1, they're in common for the numerator and denominator. So I can split the numerator. So this is 1 plus fn minus 2 over fn minus 1. So let me quickly do this. So here, remember, I can divide both top and bottom by fn minus 2 so that the denominator becomes the same type of ratio, okay? So this is fn minus 1 over fn minus 2. So if you look at the pattern, this convergence, right? So this fn over fn minus 1 converges to, let's say, some phi, okay? So now this in terms of limits, right? So this thing will go to phi. This denominator also goes to phi, right? When n gets larger and larger. So this is actually a quadratic equation. This is phi equals to 1 plus 1 over phi. Right? So if I multiply both sides by phi, it's going to be what? It's going to be phi squared equals to phi plus 1. And you can solve this, right? So phi here equals to, so this phi squared minus phi minus 1 equals to 0. So phi has to be 2 in the denominator. The numerator is what? Is 1 plus minus square root of 4 1 squared plus 4, which is this. And actually, this number is, roughly speaking, this 1 plus square root of 5 over 2. And 1 minus square root of 5 over 2 is, it's a number that's less than 0. Okay, so it's another root that's not so reasonable, because the latter Fibonacci number is actually larger. Okay, so the ratio should be larger than 1. All right. So that's the golden ratio. Okay. So and I think the rest of the section is also talking about the uh, context of golden ratio. So you guys can read what's on the rest of the notebook. Basically, so if you have this kind of rectangular shape, okay. So if you're saying that, okay, the larger rectangle with width of a plus b and length of a, if similar to the smaller one, then that ratio you can calculate is also the golden ratio. Okay. So this you're just saying that a plus b, the longer edge over the shorter equals to the longer is a over b. So it's essentially the same thing. Okay. So if you look at the relation right there, right? So this is 1 plus b over a. That's my phi here. This is a over b, which is 1 over phi. Okay. So you can see this is the same thing. So um so the golden spiral, so this is a nice, these are nice figures that are sort of like a self similarity in the fractals. So and here I would say try this, okay? So continued fraction. So try coding this for n divisions. Okay, so this also can be defined as a recursion, right? So if you are doing the continued fraction, essentially you have infinitely many layers of divisions, right? So it's every time 1 plus 1 over 1 plus 1 over 1 plus 1 over 1 plus 1 over, and I can continue saying this without stopping. That's going to be the definition of continuous fraction. But if you say I have only one fraction, what does it mean? It means it's just 1 plus 1 over 1. And I do not have any further divisions, right? So if I want to say I have 2, then I have 1 over 1 plus 1 over and then 1 and then done. So basically it's a recursion, right? That the continuous fraction with n divisions is 1 plus 1 over the continuous fraction with n minus 1 divisions. Okay, so this is the recursion that you can build on. All right. So here, then you don't really need a lot of base cases. You only need one base case. Okay. And so yeah, this is something you can also play with and also match with the ratios that we computed earlier. So this is also not really difficult. Any questions so far? So I'm thinking, yeah. So let's look at the live coding session for this lecture 4. Wait. So yeah, think about these sort of contextual and concept questions. Okay, what's an abstraction? So what's a recursion? Recursion. Yeah, we actually coded that. Okay, so this is the cell that actually I copied from the lecture notebook, but okay, so countdown. So yeah, this is the thing that I also wrote when you guys are writing during class. So basically, you would want to make sure that your input is a positive number, right? So let's say if you're counting down from 5, you would want 5, 4, 3, 2, 1, and then blast off. So you would want your time to be positive. Okay, so let me make it if it's less than we could do, if it's less than 1. Okay, if it's less than 1, it gives me an error. So let's try that. Okay. So yeah, well, triangular numbers. Yeah, so you guys can play with that. So it's by no means sufficiently different. So I would say, okay, question 3. This one is also playing with strings. And this is something I wrote during during class from last time. So here, quickly introduction of some string manipulations. Okay, printing a string backwards and other tricks. So for this problem, we can do the following. We can use the plus operation to add two strings together. Okay, concatenate. Okay, two strings, and then if you want to know the length of a string, you can use the command len s. Okay, len s you can be used for this kind of strings to get how many characters there are. Okay, including spaces. Also, it can tell you the number of elements within a list. Okay, so this is a very helpful function. And then if you want to access the ith element, it's going to be s of I. Okay, in square brackets. So basically, if you want to get the string backwards, right, you would systematically say, okay, I put the last element up front, and for the remainder, I do recursion. Or I put the first element at the end, and then for the remainder, I do the recursion and add up front. So these are two approaches. Okay. So remember, the index starts from 0 and ends at this number -1. Okay, that's the nature of the Python indexing. So if you have a length of 10, then the indices are 0, 1, 2, all the way up to 9, and then done. So you cannot really have the string s evaluated at the index 10, because 10 is now the 11th place, which does not exist. So there's going to be a problem there. Now, if you want to get elements from ith element, as from the index I to index j minus 1, you would go from I colon j, just like the range function. So whenever there's a j, that tells you j is not going to be attained, but j minus 1 can be attained at most. So now here to write the recursion print backwards, then what I would do is, okay, here I do a hello world as a string, that's as a default string. So basically when I call the function, it will help me reverse that string. And what do I do? If the input is not a string, then I get an error. Otherwise, I get the length first. And then if the length is 0, if there's no character in there, then I would not need to do anything about the reversion, right? So here, this is the base case. And then here, the idea here is a little bit different from the lecture, that this is saying, okay, the last element, I put it up front, and then for the rest, I do print backwards. Okay, in the lecture notes that's already uploaded in the GitHub page, and in the Brightspace files, is that you can do s of 0 at the end. Okay, so can do function of as taking everything up from 1 all the way down. So if you omit the second element, that just basically just says it's going to go all the way to the end of the list, and then plus s of 0. Okay, so that's also a way which is done in the lecture notes in lecture 5, I think. So so if I let me copy this. If I change the hello ABC world, okay, so it's doing the thing as expected. And you can also say, okay, we can also, this is really similar to the n factorial recursion that we have seen, right? It's just that, okay, for the string that's going to be the input here, I just remove one element. So it's a length that's one less. So what I can also do here is to make a base case of 1. That's also fine. So if the length is 1, then do I need to do anything? I don't, right? So I can just return s. So that's also okay. Okay, uh, so for this kind of thing that's relying on the previous, then 0, 1, they can all be base cases. So the same thing here. Okay, so that's totally fine. All right. So so basically, I was having a bug when I tried to get an error message for a string of length 0, and then I was debugging, but this implementation was on the screen for a few minutes, and I didn't have the time to talk about it. But yeah, make sure to play with your implementation and then fix whatever error that it encounters. Okay, so it's a very useful practice opportunity. Question? Okay, yeah. So you guys can play with uh, whether a number is prime or not. Okay, so this is question 4. So I think I have. Oh, okay. I don't have anything here. Good. So this is basically saying, okay, I need to check whether a number is a prime or not. So what do? I don't really need to divide by the numbers larger than half of it because they are too large for factors as factors of n. Okay, so basically you just try to divide 2 all the way up to n over 2 uh, to see if any of them are factors of n. If any of them is, then that's not a prime. So basically, this is something you would want to play with, and so yeah. Um. Uh. mm, It's let's say 5 squared, 25. You need to try 2, 3, 4, 5. Then okay, 5. So it's not. So you see. So yeah, it's really up to it's really about what kind of. So you do need to have a few trials in order to get to the conclusion. Like 7 squared, 11 squared. So that's the problem. So yeah, you may not really need up to n over 2. You can try up to square root of n. So that's also an option. But the idea here is relatively fundamental, and you could play with that. But then you need to think about some potential issues, like if you are doing 2, right, and then n over 2 is 1. So if you're going from 2 to n over 2, then maybe that n over 2 is not even larger than 2. So there are certain small issues that you need to take care of when you are writing this kind of for loop. Okay, so this is definitely a for loop. Whenever there's whenever you get a whole number out of the division, then you would change the status from not prime to not prime. So at the end, return something. So yeah, we can talk about it on Wednesday when we come back. But make sure to play with this one. Okay.
So on Wednesday, you will go through each questions, right?
We need to
Or
all
just the
cover this one.
Can we also do third?
Oh, do we? Oh,
I mean, we've already done it, but
yeah, yeah, yeah. The notes in the notes, there's one doing the other way. So which well either way is fine. So
okay.
yeah. So let me see. Let me quickly see that. Uh,
Is it okay if my daughter comes to class with me on Wednesday? Would that be okay with you? She's in first grade and I'm gonna bring stuff for her to do.
You're saying to bring your
Is it okay if my daughter comes with me to class?
oh yeah, it's
Because
fine.
She has no school this week.
That's right
Yeah,
here. So this is another implementation in the fifth lecture note. Okay. Yeah.
thank you.
That's okay with you?
That's okay.
Thank you.
I had a quick question, because you, every class will take attendance, and nothing on the syllabus mentions an attendance grade.
And there's no attendance grade. It's just from our record keeping.
Oh, okay, because I was just curious about, because I joined the class late and how those.
Oh yeah.
first
It's,
few
don't worry
days
about
is-
that. Yeah,
Okay.
I just would like a relatively accurate record of that. So.
Okay, alrighty. Thank you, Professor. Thank you for your time.
Mhm.